Hi, my name is Enhao Zhang, a PhD student from University of Washington. Today, I'm happy to present our SIGMOD paper, Self-Enhancing Video Data Management System for Compositional Events with Large Language Model. Video data management systems have received increasing attention from the database community in recent years because it is getting much easier to collect and store large amounts of videos. Also, the advances in computer vision and AI have brought up many new techniques to help people understand the video contents. Data analysts working with large-scale video datasets can ask a wide variety of questions, from straightforward queries centered around object classification and detection to more complex questions about how objects interact with each other spatially and temporally. Let's consider a traffic analytics application. A traffic engineer may want to understand road hazards involving car and motorcycle interactions, such as motorcycles swerving abruptly in front of turning cars. Similarly, in the ecology field, scientists collect wildlife videos to study animal behaviors and interactions in their natural habitats. And we refer to these complex questions as compositional queries over videos, which involve recognizing objects, reasoning about relationships, and identifying attributes over space and time. In recent years, vision language models, or VLMs, have shown remarkable promise for visual question answering and other challenging vision tasks. However, they don't support video inputs natively. To work with videos, users have to provide a sequence of video frames. Moreover, their performance on compositional reasoning are still pretty low. Here is an example showing the limitation of VLMs. I provide GPT-4o an image of multiple objects and ask about the relationships between these objects. And in this example, GPT-4o fails to correctly reason about the spatial relationship between the yellow cylinder and the sine cube. Finally, deploying these large models at scale is pretty expensive. In the database community, many video data management systems are proposed to support compositional queries. The first category of research focuses on defining simple and expressive data models and query languages, enabling users to specify complex spatial and temporal patterns over unstructured videos. However, articulating such compositional queries typically requires substantial database expertise. So another line of work proposes novel techniques and user interfaces to help users express their queries more easily. And finally, executing compositional queries often requires evaluating expensive machine learning models. Therefore, recent systems also explore efficient query processing and optimization strategies that avoid materializing all intermediate results. To efficiently answer compositional queries, existing systems formulate programs or queries that decompose the task into smaller subtasks. And each subtask is handled by existing computer vision models or predefined programs. For example, an object detection model such as mask RCNN can be used to detect cars in video frames. And these systems come with built-in modules for common subtasks, and they provide extensibility through user-defined functions to address users' unique use cases. However, current systems assume the existence of UDFs for executing subtasks to answer a compositional query. For example, VSproc predefines 20 modules and creates complex programs that invoke these modules in order to make compositional visual reasoning. And EVA and equivocal execute SQL queries, which contain UDFs in their predicates. However, manually providing these UDFs is a big burden for users. To address these limitations, we present VOCAL-UDF, a self-enhancing video data management system for compositional events. VOCAL-UDF can detect what UDFs are needed based on user queries, automatically generates the necessary UDFs, and execute queries with these generated UDFs to find matching videos. And to achieve this, VOCAL-UDF leverages LLMs and VLMs. However, there are several challenges we need to address in building the system. First, given user queries, VOCAL-UDF needs to decide what UDFs to generate. And next, VOCAL-UDF should generate UDFs for a diverse range of semantic concepts. Finally, the generated UDFs should have high quality. And in the meantime, VOCAL-UDF should also minimize user efforts. And let's see how VOCAL-UDF works. To use the system, the user initializes the system with a video dataset and optionally a set of UDFs, but not necessarily all UDFs. And we use UDFs to extract objects, identify relationships and attributes from videos. And they can be captured into the objects, relationships, and attributes relational schema. And the frames table stores the image pixels of each frame. These UDFs take the relations as inputs, which includes objects, relationships, and attributes that are already extracted, and also the pixels. The user issues a query in natural language. In this example, they ask for a car that is initially in front of another car and then drives to be behind it. The system parses the query into a domain-specific language, or DSL, using the available UDFs. And in the DSL, each variable OI represents a different object. The parts before the semicolon says that in a frame of the video, there should be two cars, O1 and O2, and O1 is in front of O2. The part after the semicolon says that in another frame of the video, the car O1 is behind the car O2, and the semicolon further indicates that the second part of the query happens sometime after the first part. The system then compiles the DSL into SQL query and executes it to find matching video segments. Now, the user issues another query that asks for a red car that is initially in front of another car, then drives to be behind and near that car. And in this case, this query contains predicates that cannot be resolved using existing UDFs. And our system will then automatically identify and build new UDFs. And in this paper, we assume that UDFs to extract objects are given and are used to populate the relational database. And we focus on generating UDFs to extract relationships and attributes. And I will come back later to the details of those UDFs in a few slides. And after that, we update the list of available UDFs, and then the parser reparses the query into the DSL, and finally compile it into SQL for execution. And now I will describe each component of the system in more detail. Going back to our challenges, first, given user queries, VOCAL-UDF needs to decide what UDFs to generate. And this step requires translating natural language queries into DSL and determining if new UDFs needs to be created. And we use LLMs to do this. And here is an example prompt and response. And in the prompt, we provide a list of registered UDFs that are available to the system. And in this example, the user provides a query in natural language. And since all the necessary UDFs are available, the LLM can successfully parse the query using the DSL notation. And to ensure that the generated query strictly follows the DSL grammar, we conduct a post-verification of the generated DSL to ensure syntax correctness. And this is another example where the query contains some predicates that cannot be resolved using the available UDFs. And in this case, the LLM decides to propose a new UDF called sedan, which checks whether the type of the object is a sedan. Translating queries and proposing UDFs are completely done by LLMs, and do not require any user efforts. Next, VOCAL-UDF should generate UDFs for a diverse range of semantic concepts. And to address this challenge, VOCAL-UDF supports two types of UDFs, which I will explain next. The first type of UDFs we support is program-based UDFs. So suppose the LLM has proposed to generate a behind UDF that checks whether object O0 is behind object O1. And in the most basic approach, we provide the proposed UDF description to the LLM and ask it to generate a Python program. However, if we consider the example of behind relationship, different users may interpret it in different ways. And to resolve this ambiguity, our system also asks the LLM to generate an interpretation for each program, and then generates multiple program candidates with different interpretations. For each generated program, we conduct a post-verification by executing them on a small dataset to ensure that they are executable. However, program-based UDFs don't support tasks that require understanding the visual contents of frames. Therefore, our system also supports distilled-model UDFs, which are good at visual understanding. And we use model distillation technique to distill the knowledge of a strong pre-trained model into a small model, so that the small model can mimic the behavior of the large model while being cost-effective. And to do this, we train a small multi-layer perceptron for each proposed UDF. We use the pre-trained clip model to extract features from video frames and use GPT-4o to annotate labels. Then we use the feature and label to train the model. To distill models, we need to sample video frames for labeling. However, random sampling might not give enough positive examples for training, especially when the target concept is less common. And to address this challenge, we propose an object-aware frame sampling technique. When using GPT-4o to label a concept, we ask it what objects can possibly be involved in the target concept. For example, when labeling the eating relationship, object classes like food and person are more relevant than car. After that, VOCAL-UDF filters out irrelevant objects and samples only frames that contain objects likely to be involved in the target concept. Second, our system generates UDFs that ask about relationships and attributes of specific objects in a frame, rather than concepts about the entire scene. However, there could be multiple objects in a frame, and simply asking GPT-4o whether the target concept exists in the frame might not lead to good performance. Therefore, we augment the data labeling prompt to also include object names and bounding box coordinates so that GPT-4o knows which objects in the image we're talking about. And in this figure, we are generating a distilled-model UDF for the behind relationship. And we augment the UDF description with object names, cars and truck, and their bounding box coordinates. We also draw bounding box around the two objects using different colors in the image. And again, generating both program-based and distilled-model UDFs doesn't require any user inputs. Finally, VOCAL-UDF must ensure high UDF quality. Because we use LLMs to generate UDFs, VOCAL-UDF should handle LLM errors. And also, because user provides queries in natural language, which can be ambiguous, VOCAL-UDF should also handle this ambiguity in user intent. So to address this, VOCAL-UDF introduces a UDF selection stage that first generates multiple UDF candidates, which includes multiple program-based UDF candidates with diverse interpretations, as well as distilled-model UDFs. And for each proposed UDF, we need to select one implementation that best aligns with the user's intent. To do this, VOCAL-UDF incorporates explicit user feedback to select the best candidates, and we use active learning to minimize the user efforts. Sometimes no-generated UDFs work well, and in this case, the system should not apply a UDF that can negatively affect performance. To prevent this, we introduce dummy UDFs in candidates. They are functions that simply return true. And VOCAL-UDF will fall back to using dummy UDFs when no other candidates perform well. Going back to our example query, where the user looks for a red car that is initially in front of the another car and then drive to be behind and near to the car. And the VOCAL-UDF can execute this query even when the necessary UDFs to detect red colors and near relationships are unavailable, by automatically identifying and generating them with high quality. Since the generated UDFs are not perfect, VOCAL-UDF can still return videos where the car is not red or the two cars are not close to each other. We evaluate VOCAL-UDF on 3 datasets. And in this talk, I will show results on the Clever dataset, which is a synthetic video dataset consisting of multiple objects moving around. We also evaluate on 2 real-world datasets, CTFlow-NL and charades, and we have these results in our paper. We compare VOCAL-UDF against 2 baseline systems, VisProc and Equivocal. Both systems support compositional queries, but don't have the ability to generate new UDFs. When evaluating each system, the inputs include a video dataset, a natural language query, and a set of available UDFs. The system will answer the query by outputting a set of matching videos. When generating each UDF, we use GPT-4o to annotate 100 samples for distilled-model UDF generation, and ask for 20 user labels during UDF selection. We evaluate the performance of each system on the Clever datasets. We vary the number of new UDFs that needs to be generated to answer a query. The x-axis shows the number of missing UDFs, ranging from 0 missing UDFs to at most 3 missing UDFs. And the y-axis shows the F1 score of the generated query over the test datasets. And in this plot, we can see that VOCAL-UDF achieves high F1 scores even when UDFs are missing. And the baseline systems perform worse as they cannot generate new UDFs. We also compare VOCAL-UDF with direct LLM approaches. For the vanilla LLM approach, we provide GPT-4o a sequence of video frames and directly ask whether the target event occurs in the sequence of frames. And the results show that VOCAL-UDF achieves higher F1 scores than using GPT-4o directly. And we also estimate the cost of VOCAL-UDF and 2 direct LLM methods. The vanilla LLM approach is the same way that I showed in the first plot. And the LLM for concept method is similar to VOCAL-UDF, but without UDF generation. In other words, if a UDF is unavailable, we use an LLM directly as the UDF without generating new UDFs. When using GPT-4o, VOCAL-UDF only costs about 40 cents for executing one query over the full test datasets. However, the other 2 LLM methods are more than $200 and $1,500 for executing just one query. Therefore, VOCAL-UDF is more cost-effective than direct LLM baselines. In conclusion, in this paper, we present VOCAL-UDF, a self-enhancing system that empowers users to issue compositional queries even when UDFs necessary to answer the queries are unavailable. And for more details, please visit our project website, and we also make our source code publicly available. Thanks for watching.